So what makes a gas a greenhouse gas? Why aren't the two most prevalent gases in the atmosphere, nitrogen and oxygen, N2 and O2, greenhouse gases? To answer this question, we need to look at molecular shapes and how that defines how they absorb radiation. To understand shape, we need to be able to draw molecules. A very simplistic pictorial understanding of where the electrons are in an atom are given by what's called a Lewis symbol or electron dot symbol. The symbol represents the nucleus and core electrons, here, here, and the dots represent single electrons. The four regions around the symbol accommodate 2 electrons apiece. And then we see some symbols for some representative elements given in this table, table 8.1. This is from a different textbook. Elements in the same group have the same number and arrangement of valence electrons. We've talked about this before. For example, if we look at oxygen, he is in group 6A. He has, well, that's the valence electrons of his, and we're not really going to worry about this electron configuration. That's more advanced than we have to worry about. We're just going to worry about him. So we put the symbol, and that represents the core of the atom, and then we start adding electrons in the outermost area. These are called the valence electrons. Valence electrons are those found in the outermost volume. Of an atom. And these are the ones involved in bonding. So that's why we care about them. Bonding with other atoms. All right, so we'll start off with O for oxygen, and then we start adding our 6 valence electrons. We go 1. We don't pair them up until we've put 1 in each side. Right? And then we have 2 more, and it doesn't really matter where they go. All we're looking at is the number of paired versus unpaired. The number of electrons available for bonding are indicated by unpaired dots. So we find that oxygen will form 2 bonds. And we've seen this occur in O2. Right? Those are 2 bonds. We keep going, adding electrons as we go across a row, and at the end we have our noble gas. In this case, neon. And you'll notice a noble gas has 8 valence electrons. 8 electrons in the outer shell, the valence shell, valence area, and you'll notice they're all nicely paired up. This is a very stable configuration. And you'll remember that noble gases don't bond with anybody. So this also shows why that is. Right? Now we can assume that an atom is stable when surrounded by 8 electrons, 4 electron pairs. So how do we draw Lewis structures? For molecules, we will take a number of steps. We add up the total valence electrons, which is going to be the group number for our main group, remember our A group, for each one of the atoms in the molecule. Then we're going to identify the central atom, usually first in the formula. We're going to arrange the atoms in a skeletal structure and connect them with a single bond, that is 1 pair of electrons between each set of atoms. Then we complete the octet, 8 electrons around the terminal atoms. Those are the ones at the ends. We only use 2 electrons for hydrogen. That's all hydrogen can hold, so he's the one exception. And then we're going to place the remaining electrons on the central atom. If the central atom does not have an octet, we're going to use lone pairs from those terminal atoms to form multiple bonds. Okay. So many structures of covalently bonded molecules can be represented by Lewis structures. Let's do some examples. Let's look at methane, CH4. Carbon is in group 4A. He's got 4 valence electrons, 4 electrons from him. And the hydrogen is in group 1A. He has 1 valence electron, but there are 4 of him. So we have total of 8 electrons. We're going to put carbon in the center. Usually the first one is going to be the central atom, but we know it has to be because hydrogen can only form 1 bond. Now we do a skeletal structure with hydrogen, single bonds, and then let's account for the number of electrons we've used. Each one of these dashes is 2 electrons, so I have 2, 4, 6, 8 electrons, all accounted for. This is what I started with, so they're all accounted for. And hydrogen has 2 electrons, he's happy. And carbon has got 2, 4, 6, 8 electrons, so carbon is also happy with an octet. Okay, now if this was CCl4, where I've put chlorines in the place of hydrogen, I still have 4 electrons from my friend here, he's 4A, but now chlorine is a halogen, he's in group 7A. So I'd have 4 times 7 electrons, and this would be 28 plus 4, 32 electrons. Same process though. We're going to do carbon in the middle. The terminal atoms are the chlorines. You'll notice I do this as a little cursive just to show you that the L is with the C. Okay, now the fourth rule told us to complete the octet of the terminal atoms. So let's start adding electrons here. Remember the dash is 2 electrons, a single bond. Okay, so now we've completed the octets around chlorine. Let's add them up. We've got 4 terminal atoms, each with an octet, so that's used up 32 electrons. That is how many we started with. Let's see now if so we've used all the electrons available. Let's see if everybody's happy. The chlorines have octets, yay! The carbon, he also has an octet, so he's happy. So we are done. Done and done. Okay, let's try something. Let's try NH3, ammonia. Same process. He's a 5A and a 1A. So I have 5 electrons from the nitrogen plus 3 times 1 electron from the hydrogen. This gives me 8 electrons. This is how many I have to place. Nitrogen in the middle, hydrogen, and single bonds, and hydrogen can only hold 2. So how many have I used up? 2, 4, 6. I started with 8 electrons. I have placed 6 electrons in bonds, and I end up with 2 electrons left over. According to our rules, we're going to put that on the central atom. And that's hunky-dory because now my nitrogen has an octet. Okay, let's try CO2. 4A, 6A. So I've got 4 electrons from the carbon plus 2 times 6 electrons from the oxygen. This gives me 12 plus 4, 16 electrons. Okay, let's do our thing. Carbon in the middle because he was first. Single bonds to the oxygens. Next, we complete the octets around oxygen. So the oxygens are happy. They've got octets. But what about poor little carbon? He only has 4 electrons around him, 2 in each of those bonds. Let's see where we are. We start off with 16 electrons. We have 2 terminal atoms, each with 18. So we subtract 18 electrons for our valence electrons. I'm sorry, for our terminal atoms. That's, oh my goodness, we have no electrons left, but carbon is not happy. He does not have 8 electrons. So what do? We're going to take the lone pairs from oxygen and make double bonds to carbon. Here to here, and it doesn't matter if these are all this here to here. What does that do? Well, it doesn't hurt oxygen. He's still, whenever we have a bond between 2 atoms, they're considered to be part of both atoms. Okay? So if I put these 2 on into a double bond there, those 4 electrons are considered to be part and parcel of the carbon and the oxygen. So you share, but you don't lose anything, which is very, very nice. And he still has 2, 4, 2, 4. So is everybody happy? Yep. Carbon's got 8 electrons. Oxygen over here has 8 electrons. And the oxygen over here has 8 electrons. Great. All right, so now we know how to make Lewis structures of simple molecules.